Hi, everybody. Welcome to the third annual CRESTEM Keynote lecture. It's the first time that we've gone hybrid. The previous two keynotes were kind of in the midst and end of the pandemic and were completely online. So it's lovely to have people with us in the room today, as well as all of those of you who have been able to join us online. Before I introduce tonight's guest speaker, I just want to say a little bit about CRESTEM, and particularly some of the CRESTEM activities that people who have come today, either in person or online, might be interested in joining us in. CRESTEM stands for the Centre for Research in Education in Science, Technology, Engineering and Mathematics. We have monthly seminars, and anybody who is interested in taking part in those seminars can write to me. I'm Lulu Healy, and you will be added to the CRESTEM seminar list. We also like to take the opportunity of the keynote every year to remind people of two different courses that are offered within the domain of CRESTEM here at King's. One is the MA STEM education course, which we have been very fortunate in receiving funding in the form of bursaries for practicing teachers from Wipro, an Indian information technology company. I think that if you go online and look at the CRESTEM page and choose the scholarship tab, you will be directed to how to apply for those bursaries. We've been very proud so far that the bursaries have funded practicing teachers not only from London but from all over the country, as we have organised this course in a way that people can participate online as well as coming to weekend in-person sessions. And one mark of the success, perhaps, of the course so far is the number of graduates who have been interested in carrying on with their studies and applying to do a PhD within the CRESTEM Centre. We're also very fortunate that we have a science education dedicated PhD scholarship, the Ros Driver Scholarship, and more information about that is also available on the CRESTEM page. CRESTEM brings together King's has had a very long history, actually, of research in mathematics education, in science education, and in computing education. But CRESTEM brings us all together in one group, and we like to think that the whole is a little bit greater than the sum of all the parts. We were very fortunate that until relatively recently, today's speaker was a member of our CRESTEM family. And we are really, really pleased to be able to welcome her back today. It's my enormous privilege to be able to introduce this year's keynote presenter, Sentance. She's currently the director of the Raspberry Pi Computing Education Research Centre at the University of Cambridge, which was established by her in 2021 to increase our understanding of the teaching and learning of computing. She has also been the Chief Learning Officer at Raspberry Pi Foundation, where she acted as a senior advisor on teaching and learning and led the educational research programme. She's also played a leading role in the National Centre for Computing Education. In 2020, Sue's a prize winner. In 2020, she was awarded a Suffrage Science Award for her maths and computing, and in 2017, the bearer Public Engagement and Impact Award for her services to computing education. We're very lucky that she has remained a visiting fellow here at KCL. On a more personal note, I have had the great pleasure of jointly supervising two PhD students with Sue, one of whom is our colleague Alex, who's sitting in the room today. Sue's huge commitment to computing education is simply contagious. with the result that she attracts collaborators and students of the highest calibre to work with her, while at the same time displaying an inclusivity that nurtures those who are just beginning in the field. Welcome back to King's, Sue. You have been deeply missed. And as you said, it's a bit like old times. Over to you.
It's lovely. Thank you very much. I am indeed honoured to be asked to come back and give this talk. And it's been just a pleasure to stay connected with King's since I left in 2018. And thank you all for coming along. And thanks to everybody online. I can't see at the moment, but I think there are some people online. I'm going to be talking to you about, as Lou says, I have a bit of a passion for computing education. So we're talking about computing education. Hopefully, if you weren't convinced already that it's incredibly important to be everywhere in the world for everybody, and a really core part of our curriculum. We've had a lot in the press at the moment recently about ChatGPT. I can't even say it. ChatGPT and machine learning generation, and so technology and AI and its relationship with education has been on everybody's. People have been talking about it a lot, and this is a real inflection point. It's not the topic of my talk, but I think it reinforces the fact that learning about computing in school is really important, and we need to really make it a priority. So let me find my slides. Perfect. Okay. So I'm going to be talking about a few things today. I'm standing, if you're not online, I'm standing between you and all these filled wine glasses. Despite the fact there are 5 things on this list, my talk is in 3 parts. So I want to talk, first of all, around setting the scene. Some of you may not be as familiar with computing education as I am. I want to talk about a sort of global situation of computing around the world, the history of computing in England, and what we actually teach in school. That's the first 3 things, and that's my first part. I then want to talk about what I put there as some bottlenecks and sticky points. I want to talk about some of the issues that I can see. If you're a teacher in computing, you may have completely different issues, but these are some of the things that bother me. And I really want to finish by thinking a little bit laterally about computing education and where possibly we could be thinking a little bit differently about how we approach computing in school. So that's the outline. So let's start off, as I said, about thinking globally. So computing education has become very important to lots of different countries. And the Brookings Institution, which is a think tank in New York, did a project that lasted 2 years where they looked at the state of computing education, where it was in school all around the world. And they also did some in-depth case studies. And I think you can see from this picture that it's patchy. It's still patchy. The dark blue means that there is mandatory computing education. Light blue means that it's in either primary or secondary. Green, I think, is elective. Yellow is for some children. And grey is really still on its way. So there is obviously a lot still to do. But this, what is interesting is that think tanks like the Brookings Institution are interested in the fact that we should be thinking about the education of young people around technology and computer science. Let's dig a little bit deeper if you look at US. So the US does not have a national curriculum. It has different curricula by state level, district level, sometimes even school level. So, but there's a lot of investment gone into developing computer science there, and there's quite a lot of monitoring of how much the take-up is. And now there 53% of US high schools now offer foundational computer science. So they see that as a quite a big win because they've tipped over the 50%. But still, it's not offered as much to rural schools, and it's less available for of course, students of different backgrounds, as you can see on the slide. So let's look at Europe. So in Europe, also, there's a lot of monitoring going about how, is computer science appearing in the curriculum? And there's an initiative called Informatics for All, which is like a group of people from different countries who have signed something called the Rome Declaration, where they've all committed to bringing computer science into schools in those countries. And they call it informatics. We call it computing or computer science. And a report that came out at the end of 2022 was reported on the state of 39 countries in Europe. So out of 39, 38 are offering computer science or informatics in some way, and but 23 in primary. And the different colours refer to whether it's mandatory or whether it's integrated in the curriculum. So you can see that this is really a world issue. Everybody's interested in educating young people around computing in school from an early age. But we still have to answer this question, why? Now, colleagues in CRESTEM, in maths education and science education, you don't have to defend your subjects as much as we do. We have to keep saying why we need to have computing education in school, why it's so important. Whereas I think, in more established subjects in the curriculum, you haven't got to keep justifying your existence. But there are many arguments, and these are only just a few of them. And the economic argument, if you think about in the macroeconomic argument, is that countries with computer science education or IT, more IT graduates do better in terms of their GDP. The microeconomic argument is that individuals with their opportunities do better. The inequality argument is huge, that countries where it's been offered are there are narrowed income gaps between countries that do and don't offer technology and computer science education. And there's also the basic idea that we need to be educated in computing, and that we also we need our young people to be able to exercise digital responsibility, especially in the rapid change that we're seeing at the moment. So, having answered the question of why, there are some still things that we all disagree with or not argue about, debate in countries or internationally. So these three questions, and I'm going to give you my answer to these questions on my last slide. So is computing in school for everybody or just for some? What age should you start learning it? And should it be taught as a separate subject, or should you teach it integrated in the curriculum like they do in Sweden and France? And there are different answers in different countries for these questions. But these are the things we're still trying to agree on. And in this, the yellow box you can see that's appeared on the right-hand side, these are some indicators that the Brookings Institution published to show how well a country is doing in integrating and getting computer science into the curriculum. And just to tell you that England has got 7 ticks across these. So the first few are about, is the subject in the curriculum? That's the first 3. These 2 here are around, do we educate teachers to teach computer science either before they go into teaching or while they're in computing? And the last 2, I think they wrote these especially because of the National Centre for Computing Education, have a specialised centre or institution focused on CS education research and regular funding from the government. And in the Brookings Institution report, they've shown where some of the different countries are. And England, we are very fortunate that here we have mandatory computing for all children from age 5 to 16, or at least 14, where they choose their options. And we do have in-service training. We do have the National Centre for Computing Education. And I'm going to look a little bit about England in more detail, starting with a little bit of history, because we in England have been looking at computing education for quite a long time. It's not new. So if you look at this graph, notice that I didn't start over on the left. So in 2018, we've got this increased investment in the National Centre for Computing Education. We have a lot of investment from the government in computing. And that's 10 years since Computing at School was formed as a grassroots group of teachers and other stakeholders to really advocate for computing in the curriculum. So it's, that's a sort of a 10-year gap in order to get from really, lobbying for computing and then having this great investment that we have now to really support the subject. And in 2014, we had the new curriculum because there was an overhaul of curricula at that time, and computing became a subject in its own right. But that's just the recent history. I was teaching computing in 1999. We had A-level computing from at least 1969 in England, which is pretty amazing because we only started doing university courses in the sort of the debatable about whether the 50s and 60s, but certainly really up and running in the sort of late 60s, early 70s. And I found a lovely article by Jackie Griffin, written in 1989, who was talking about the new GCSE computer studies, who said that most schools are offering computer science, at least in computer studies, at least in years 4 and 5. That was in 1989. So we have been doing this for quite a long time. We've switched to ICT when the personal computer came in and we needed to understand more about being a user and applications. And then we swung back to doing more, including computer science. But we are still really not agreed completely about how we teach computing, what we teach in school. And I think we've been at this for a long time. We should know the answer to this by now. So let's look at what we actually teach. What is the subject that we teach? And I'll go back to my title, which was about astronomy and telescopes, which was the allegedly said by Edgar Dijkstra, who was a Dutch computer scientist in the 1970s, who wrote algorithms and devised the shortest path algorithm that helps you get around lots of places in the most efficient time. So very clever. And but he said, apparently, computer science is no more about computers than astronomy is about telescopes. So let's try and look at that analogy. So astronomy is a discipline, it's a subject, and a telescope is what you use to use as a tool that you use when you're doing astronomy. So you follow that through. Computer science is the discipline, it's the subject, and the computer is the tool that you use when you're doing computer science. Doesn't quite work because actually computer is the tool that you use when you're doing everything, actually, at the moment. I wondered if I put stars there. Astronomy is the discipline, and stars are the things that you're studying, then computers are the things that you're studying. So it sort of works, but the idea behind it, the idea that that was intended, was that we shouldn't be thinking about the computer as much as thinking about the principles of the discipline. And I agree with that. But computer science was originally about how the computer worked, because that was what computer science was. It was about how the computer worked, and then it moved into how all the computers worked. So it became more general and more principles came out. So I think there's a little bit problem. There are some, I have some issues with this analogy in that I don't think we should be using this to say that we only think about the principles of our discipline, and we don't think about technology, because we do need to think about technology. So now I'm going to go into some detail about the sort of topics that are taught if you are studying computing in school. Now, in the middle here is an infographic that I've explained on either side, but this is a computing taxonomy that's been developed by the Raspberry Pi Foundation, and it originally came from looking at the curriculum in England and looking at what was in the national curriculum, what was in the GCSE computer science, what was in the A-level computer science, and then looking at how we could do some synthesis to pull out the core topics. And the reason, and now it's being developed more internationally, and artificial intelligence, which is not in England's curriculum, has been added to the list of topics. But the reason I want to show you this, because it's interesting, is that we've got discrete topics. We think if you're in a science or maths, think about your own topics. We have discrete topics that we teach there on the left-hand side, but then we have these strands, and they go across all the topics. They give us some breadth. We should be thinking about the impact of technology all the time that we're teaching any of these topics. We should be thinking about safety and security all the time. And that's what new about this way of interpreting the curriculum content. So I taught A-level computing and GCSE ICT. I remember I used to have one lesson on computer architecture, then a few weeks later I'd have some lessons on programming, and then a few weeks later I'd have to teach about ethical issues in computing, completely divorced from anything else that I'd been teaching. It was all separated out, but now we've got this idea of breadth. Let's look around the world. So you can see the topics that what we're teaching in England. Look at the US. So they have a different approach. They have some topics, but they also have practices. We don't have any practices. And look at these practices. I'm going to say lovely practices, it's not very academic, isn't it? Right at the top, fostering an inclusive computing culture. That's written in the framework for the subject. That's what all students need to learn to do. We don't have that. We don't have about collaborating, communicating about computing. And we don't think about defining computational problems. So there's some things that we can learn from other countries. Let's look at the European approach, the Informatics reference framework. So they have 11 topics. If you looked at them briefly, you'd think, oh, they're very similar to the taxonomy I showed you before. We don't have any human-computer interaction. You know, how does the computer and the human interact with each other? And we don't really think about responsibility and empowerment. So I think there are bits that we can learn from thinking about computing education internationally and looking at what others are doing. So let's look at what we do teach, GCSE computer science. Here's some extracts. So I have to get a bit closer to look at these. So I just pulled out some elements of the GCSE curriculum specification from AQA. We have to explain, students have to explain what data compression is, and they have to know about Hoffman coding now. And they have to know about binary numbers, and they have to know about run length encoding, all that stuff. Okay? And then it's the teacher's job to try and make this relevant to the student so that they can actually relate that to something that is in their world, unless they want to teach it completely standalone. And actually, if you look at here is the A-level computing in 1971. So we were learning quite a lot of the same things. We were learning the principles of Boolean algebra. We were doing binary numbers. We were looking at computer hardware. So there's a lot of things in the 1971 A-level curriculum that are still taught at GCSE and A-level. That's because we're focusing on the principles of the subject and the discipline and the things that don't change around computing, the sort of the rules around the system. And there's quite a lot, and I think this is quite good, there's a lot of maths. And the maths is quite hard. So I don't think our A-level students have to do that anymore. So the point I'm trying to get is that we have made a conscious decision in England to teach about the principles of the discipline, the concepts, that don't change. I started studying computer science. I don't know if I should say this shows how ancient I am. I started studying computer science in 1980. And a lot of the things at the university and a lot of the things are there that I studied. But the world has moved on. The world's moving on all the time. So how can we connect young people? How can we connect these principles to the experience in the real world of our young people? And I'm just coming to the end of this first part. I won't dwell on this for too long, but the reason that we teach in this particular way is we have a particular approach in England called the knowledge-rich curriculum. For those of you who don't know, education is devolved. So Scotland and Wales do not claim to have a knowledge-rich curriculum. We have different kind of curricula. And this dictates the way that we teach and the focus that we have on knowledge and facts. And politicians and ministers who have been responsible for education have said that they're inspired by E.D. Hirsch, who's a very well-known US a writer about education, and the focus is on accessing facts, building facts on more facts, and structuring facts well and knowledge. Now, I don't want to dwell on that for too long, but it does influence. You can see the influence on it on what we have to teach here. So I'm now going to talk a little bit about issues in computing education. So I've finished my first part. I don't know if I'm on time. I finished my first part. I'll do a little recap. So my recap is everybody in the world wants to teach computer science now. It's shown as really important. We're almost at the point where we can stop defending why we have to have it in school. So we have these three questions. We teach the astronomy equivalent at GCSE and A-level. We teach the discipline, the principles. We don't teach so much about the computer and the technology. So let's look at some issues in computing education that occurred to me when I was thinking about this talk, which I was invited to do nearly a year ago. So it's quite. I'm pleased that what I'm talking about is roughly what I said I'd talk about last June. So I want to talk about computing for all is still an issue, achieving computing for everybody. The terminology is an issue. When I put AI, etc., I mean, there is new stuff that's not on our curriculum and the lack of research. So I'm going to focus on those things for the next sort of 5 minutes or so. So I'm not going to start at the beginning because that's too linear. I'm going to start with terminology. So terminology, what is the problem with terminology in computing? If anyone's been listening, they might notice that I've been using computing and computer science completely interchangeably on purpose, even though we make quite a distinction in this country about the difference between computing and computer science. So I love this quote. There's a nice article written by Clark and Boyle back in 2006. It's called something like, I can't remember which way round it is. We lost the S and now we're losing the C, or we lost the C and now we're losing the S. It's bemoaning the state of computing, of computer studies. So, but what they say is where computing is special is being the victim of a terminological and political confusing that is to the detriment of education. And I think that is the case, that we do get muddled up about what we call our subject. We sometimes call it computing, computer science. ICT is still in some schools. Digital competencies in Wales, computing sciences in Scotland, computer studies is still all around the world, and was what we used to call it. So we do, and when I'm a researcher, I write papers and I write about the curriculum, I have to have a massive big footnote at the bottom, Jane's laughing, because it takes about half a page trying to explain what you mean by all these subjects. And I'm fed up with having to explain what I mean about all these different terms. Why can't we just call it all computing? So the Royal Society did a great thing in publishing the Shutdown or Restart report in 2012. That got us all going and got computing into the curriculum. But there is this diagram in the Shutdown or Restart report. It says, let's not have ICT, let's have this thing, which is called computing. And it's a combination of computer science, information technology, and digital literacy. And what are the bits in the middle? Anyway. So that was very useful at the time. It was very useful at the time because we then could see that what we had in computing, when we were teaching about computer science, we were just adding to what we already had. So we were saying that, in the subjects of computing, we're going to have some new elements of computer science, but we also will keep teaching ICT and digital literacy. So that was the intention, and that was very helpful at the time. I don't think we need that anymore. I think that it irritates me, intensely when I hear people start saying that there are three aspects of computing, because if you listen to people in other areas of the world, computing is a subject that is the same as computer science, and it's just used slightly, the terms are used interchangeably. Peter Denning taught us about the 7 great principles of computing, not computer science: automation, communication, computation. Computing as a discipline, the ACM is the Association of Computing Machinery, not computer science machinery. So I think this is a little bit not needed so much now to make this distinction. And then, of course, over there we have computational thinking. Now, I'm not going to talk about computational thinking because that would take another 20 minutes. But computational thinking is yet another term that we have to use. And if you listen internationally to the debate, it's a very useful term for countries that are new to computing, trying to get computing into the curriculum, to convince their governments and say that computational, we need all our young people to think computationally, like they think mathematically and scientifically and engineeringly. It has its uses, computational thinking, but there are about 3,000 definitions of the term computational thinking. And when we got computing into the curriculum, we realised you can't explicitly teach or assess computational thinking in itself. We now just talk about computing and the actual things that we teach. So we have a terminology problem. But let's go to my second issue, which is computing for all. And this is something I really care about. My interest is that we can reach every young person in the world with computing, to give them the opportunities and the discourse and the life that they need by living in a society that is so rapidly changing in terms of technology. And we have a mandatory computing curriculum in England from age 5. So we are the lucky ones. We have this in the curriculum. And in time, possibly, we have those children who've studied it through school will be parents and be teachers and run businesses. And then we might find that we start to think of computing being a little more accessible to everyone. But right now, we're not really achieving that. Computing is still white and male. And this slide, thank you very much, Jane, back of the room, for this slide that I pinched off your other presentation. This slide gives some facts and figures, just showing us, the percentages of Black people, female, in work and in university and in school. And here I've broken this down a little bit more. So we are making progress with A-level. You can see A-level from people who took it in 2018 going up to 15% to people who took the A-level in 2022. 15% of them were girls. GCSE, the advanced was a little bit more slow, but we still have a shocking gender balance issue in computing. I thought this was interesting. So this is from the Clark and Boyle I told you about earlier. I don't know if you can see their little dots. So this is female engagement, females taking A-level computing 1968 to 1999. So I didn't do A-level computing. It wasn't offered in my school, but I started computing in 1980 and look, it was like 24% or something. And I definitely, when I was at school, when I started in Edinburgh, I didn't notice a gender issue. I mean, it wasn't something that was particularly pertinent to me. And then we got this massive drop. I thought that was interesting. I don't have an interpretation for that, but you can go away and work out why did female A-level drop in for between 1980 and 1990 so drastically. So we're working our way back up again. So what we do is we need to be thinking about our pedagogy so that because if we can't change the curriculum, we need to change the way that we teach so that we make our teaching inclusive of everybody. So we've been doing some work at the Raspberry Pi Foundation and at the university around trying to support teachers developing culturally relevant pedagogy into the computing curriculum, and some people in the room have been involved with that. But what we want to do is we want to ensure that voices, contexts, and experiences are considered in the lessons that we teach, and make computing in school relevant and meaningful to our learners. So, and that's because, maybe save that bit for later, but we need to adopt culture relevant computing by Heather, because the curriculum that we have is not already, the relevance is not embedded into the curriculum. So now I'm slowing down a bit. So AI, etc. So the point I'm saying here is that we have a computing curriculum that was written in 2013, and there will be things maybe that we need to refresh in our curriculum. And the government, fortunately, is very keen on making sure that all young people understand about AI. So the bit on the left is a quote from Chris Philp, who then was the UK Minister for Tech and Digital Economy, who came to do a panel session for us at the Raspberry Pi Foundation, and was saying that it's so important that young people learnt about AI. In the roadmap, which is developed by an independent group of people called the AI Council, we need a comprehensive programme aimed at all teachers with a clear deadline for completion that enable each teacher to get to grips with AI concepts. That was in 2020. And the National AI Strategy says that the UK government will continue to ensure programmes that engage children with AI concepts accessible. But actually, AI is not in the curriculum. So we're talking about it quite a lot. It's not actually in the curriculum, and we need to be teaching it. And I've been to talks where people have said, oh, it's fine, it's very broad, the computing curriculum. And if you kind of turn it up this way and squint a bit, you can teach AI in this section here, but it's not in the curriculum. But there are zillions of resources to teach it. And here's another change that we don't see in the curriculum. So if you're not coming from computing education, we teach programming as we have always taught programming as you develop. You think about your problem, you decompose your problem, you write an algorithm, and then you code it. So with the new way of programming is that you have lots of data, and then you train it with the data to solve your problem as near as you can, because you have to. And in the first instance, you've got to be absolutely precise, and in the data-driven programming, you've got to be a little bit. You've got to be as close as you can. So we need a different way of teaching programming. So Matti Tedra in Finland calls that CT1, which we used to have, should now be called CT 2.0. So there are things that we still need to get into the curriculum. And the last thing I wanted to talk about was research. Now, obviously, I will talk about research. That's what I do. And CRESTEM quite unique. And King's is quite unique because they actually have computing education in an education department. And you could put on the fingers of one hand universities around the UK who have computing education in an education department. I am now in a computer science department for that reason. And it's brilliant that you do, because you get that crossover. You learn from maths education and science education, and that's really important. So well done, CRESTEM. So, but we don't have, because of this, it's not in education, it's not in computer science, it's not funded by ESRC, it's not funded by EPSRC. We do have a problem with getting funding for research, and we have a low capacity. So I just did a little study. I looked at the Ref 21, I looked at all the impact case studies. There are lots in computer science, there are lots in education, there are lots in engineering, and I counted, you might dispute my counting if you want to read 600, 800 case studies, 4, one of which is Greenfoot, Michael from Kent. But yeah, 4 impact case studies about computing education. So either there's lots of computing education, it's not having any impact, or I think the actual fact is there isn't really very much research going on in this country. However, in the US, there's loads. There's lots of computer education. The field is really growing for young people. And you can, Barack Obama made a commitment to fund, it was called computational thinking, computing in 2006 or 8 or something like that. And lots of millions have been spent by the National Science Foundation on projects in universities and associated organizations. And now all the people who have been funded by those grants are popping out of the system with PhDs and becoming researchers and professors. And so there's lots in in the US. In Germany, there's always been a strong tradition about computer science education. There are, I don't know how many computer science education professorships. Some of them are vacant. There's so many. So if you are a researcher in Germany, there is a trajectory. You do your PhD, there is a post for you to go to in computing education research. And in this country, you've got no chance, literally. So I don't think I'm going to bother too much about this slide because it looks like it's very complicated. But I always find a place for this slide in every presentation that I do, seemingly. But this is just demonstrating that there is a lot of research going on, and there's a lot of stuff to research. We do need. In the next slide, I'll talk about some of the research questions that we have, and I divide it into these 4 sections. But basically, there are lots of things that we need to be thinking about from a research perspective in order to make the computing and learning, the teaching and learning of computing better. So here are some questions. Now, I don't intend for you to read all of those questions, but Don Passy in 2017 wrote a really nice article, which has lots of reasons why we should teach computing in school. And secondly, at the back of it, has about 3 pages of research questions that we should be asking about, that we should be researching in this country about computing. So what kind of pedagogy should teachers deploy? How can schools just develop their curricula? How can we make computing engaging for everybody? So there are a lot of questions there, and there are more besides. But we don't have the capacity to do the research here. We just don't have the infrastructure. But actually, probably right this moment, well, not this moment because it's the Easter holidays, there are around 4 million children in England studying computing. We've got lots of research participants, and we could potentially really shift the needle on pedagogy, assessment, curriculum, and equity. But we have a low capacity, as I've said. And I'm doing my bit. I won't plug my research centre for too long, but I'm doing my bit. We've started a small research centre with an absolute focus on computing education for young people, and hopefully will start to have an impact at some point. So those are my those are my two parts. So in the second part, I talked about issues that I can see in the ecosystem. Terminology is a mess. We're not teaching. Things are popping up that think the world's moving on, and we're not really addressing those issues. We need to make sure there's a better representation in computing, and we need more research. And then I wanted to finish my last 10 minutes. I wanted to finish by, can we think a little bit more laterally about all of these things? So are we teaching the right things? Are we teaching it in the right way? Do we have the right goals for computing education? So I want to think about it, and I'm going to refer to the work of other people, because my own thinking is really an early stage in some of these ideas. So I want to think about linking society and the individual to computing as a discipline. So we do sometimes think about computer science, the hard stuff. Oh, computer science is really hard. And then, students should do digital literacy. And there's also something sort of a bit woolly and easy about that, just like using the computer. And then we have many more people doing it and blah, 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 blah. So I don't think that we shouldn't be calling these things hard and easy. And secondly, why aren't we teaching them together? Why aren't we looking at the implications and the ability to make critical decisions and things around technology at the same time as we're teaching about the principles? So we need to join these together. So I'm now going to show you 3 quotes that I've taken from other people's work that I think will invite you to think a little bit differently about this issue. The first one brings out visual aid. Here we are on Zoom. If anybody, I've just got a new edition of my edited book. So I've given it to Alex, but he's allowed me to hold it up. There's a chapter in there written by Carlson Short and colleagues from the University of Paderborn called the Ariadne Principle, and I'm going to talk about that later on. And it's around how the relation of computing to the world around us. So if you look at the bit in bold, and he's saying that as well as learning about the architecture, the system, the principles, the discipline, the core concepts, the stuff that hasn't changed since I went to university in 1980, that stuff, as well as learning that stuff, has to be integrated into investigations into how and where digital technology surrounds us, how we use it, and how it affects almost every aspect of life. Sounds quite sensible to me. Here's a second quote. Now, this one is by Enrico Nardelli, who's a professor of computer science in Italy, and he's been very involved with the Informatics for All movement in Europe. Now, he's the first person to stand up and say we should learn the astronomy version of computer science. We've got to learn the principles and the concepts, and he says learn mathematics, the algorithmic, semantic systems and networks. But he's writing about digital humanism. We don't talk about digital humanism in our discourse around computing, and we should. He talks about learners should be educated to develop an appreciation for human and social viewpoints regarding digital systems. They have to tackle the challenges of digital transformation while improving social well-being of people. And given what's happened in the last 6 months in the explosion of some of our of the use of AI, given all of that, isn't that really important that we are including that in what we teach in computing? And here's my third quote is from researchers in England who, this is slightly different, who were talking about the computing curriculum aligned to values that it was bringing out in people. And they were slightly critical of the computing curriculum, saying that it was really focusing on people's self-enhancement, that it was just about getting a job. But instead, they suggested, actually, the computing curriculum could be a system to empower individuals to support a collective society, and develop individual capability that supports collective prosperity. So that kind of engagement with society and what society needs is to be really important in what we study when we study computing. And so those 3 quotes, I can share these slides. I've got all the references on there. Recommend if you're interested in this, you look at those three papers. And when I thought about this a little bit more, I'm in our discipline. There are, as I said, there are a lot of researchers in Germany, and my colleagues in Germany have talked to me about the word they use for education. And the word they use for education is Bildung. And if you do a Google Translate on Bildung, Bildung means education. But apparently, and I'm not a German speaker, it doesn't mean education. It's a mix of philosophy and education. It's about a personal transformation through education. It's around self-fulfillment, the ability to develop one's own innate capabilities, enabling us to participate in society as an autonomous and responsible citizen. It's about a journey through life. So can we teach computing like with our Bildung hats on? So I've tried to think about this, really exciting graphic. Tried to think about this, but what's computing with a Bildung perspective? We need that core disciplinary knowledge. We need to learn about networks, and we need to know about Hoffman's coding. But we also need to know about technology and artifacts and what is made. And we need to know about the relevance to the individual, and we need to know about the interaction with society. And we need to know all of those things, and they need to be sort of joined up so that I think that would make sense to a young person in school, and that would actually prepare them for the life that they're going to. So I'm going to give a little bit more theory about the work of Carsten Schultz, who wrote the chapter in the book, and then an example, and then I'm finished. Lulu hasn't started waving at me yet. So I have a lot of respect for the work of Carsten Schultz and his thinking around computer science. Some of it I don't think translates perfectly from the German system to our system. So I think we've got a piece of work to do to try and take some of those ideas and then translate them into what that means in England, in our context. But what you could take from this slide is there is a difference between structure and function, and we need to think about both. When we're thinking about network topologies and programming and some of the things, we're thinking about the structure, and the computer science we're learning is about how it works. But we need to think about what it's for. Think about what it's for. And Carsten Schultz thinks about this at different levels. So at the human to computer level, right up to the society to the computer level. And he calls this, or they call this, a hybrid interaction system. And then his thinking has gone on until the chapter that in 2023 to this thing called the Ariadne principle. And apparently Ariadne is a Greek goddess of mazes. So apparently, I don't know what this has got to do with mazes, but it's a nice thing to have a nice name for something. And A is for architecture. That's all the concepts of discipline, the key bits that we know we have to understand. I wouldn't take any of that away. What I understand about computer science. Relevance. He uses relevance into society and interaction with the individuals, which is completely opposite of what I put before. So I am interpreting madly. Relevance to societal discourses and interaction with humans. And we need to teach those within this box of what we're talking about, what we're teaching about. We need to draw in those things. And right at the top, which you can't see because the Zoom window is there, it says Genesis. And Genesis is an extra little bit on here, which is why aren't we looking at the relationships between architecture and relevance? So why is that computer system developed like that? And what impact does it have on the human that way? And then what impact does the human have on the system? And why are we not looking at the links between these? And that's really important as well. So to put that into context, I'm going to share with you one example of a unit of work that they've developed in Paderborn as part of their project, which is called ProDabi. So, and these images I've taken from a presentation that was given at the Raspberry Pi Foundation that you can see the slides of. And this is a teaching unit for grade 5 to 6, which I'm interpreting as roughly between age 10 and 12. So this is around location data in mobile communication. So we're going to start off teaching these young people. We're going to think about the mobile network. We can think about how it works, how phones work, how signals are sent, how the computer science of how this works. So we're going to do our architecture. We're then going to look at something that's relevant to society. So we're going to look at real maps and real data. We'll collect lots of data and we'll look at it all together and work out what it means and what we can learn from it. And then we'll ask lots of questions about it. And then look back at the architecture and do a sort of to and fro. And then we'll have our building. We'll be thinking about the questions that come up from this. Should we be collecting personal data? What are we using it for? All those sort of questions, the ethical questions around this. So we've looked at some computer science. We've looked at large amounts of data. We've probably programmed some of that data. We've inquired about it in lots of different ways. And then we've reflected on the meaning of it in terms of our self-view and our worldview. So I think that is a useful example of what the Ariadne principle would mean. So what about in our GCSE computer science? We think a lot about the architecture, but do we enough think about relevant society and interaction with humans? Or maybe we do, but we put them in another unit, doing a module, different module. This is module 1, and then we're talking about relevance to humans somewhere else. Why aren't we looking at it all together? So I'm going to finish now. So those are the last part was really my sort of drawing together my thoughts of what we can learn from other work that's gone on around the world. I want to leave you with a summary. So let's reimagine computing education as a curriculum that aligns principles of the discipline with their relevance to individuals and society. And let's focus on young people's being prepared for technological change and developing confidence in their computing or their computational identity. And in terms of the research agenda, we've still got all those questions that Don Pathy asked in 2017 to answer. We've got plenty of research to do, but we also could be thinking about how do learners perceive themselves and their relationship with technology? And how can teaching and learning computing engender curiosity, confidence, and capability? And I'm not saying we're not doing that, but the teachers have to do that because they need to work. They need to be able to interpret the curriculum to be able to support that. And how do we achieve? And can we use those things to achieve computing for all everywhere? And I did ask 3 questions at the beginning. You bet you don't remember what they were. It was around who should learn computing, when should they start, and is it discrete and integrated? My answers are, you can't see because my head's in the way. The answers are everybody should learn about computing. Thank you very much. We should start right at the beginning of school, and we should teach it separately in the curriculum and integrate it into everything else. And those are the answers. And the goal is to be doing that all around the world. And that's my end of my talk. Thank you.